Okay, doing Codeforces Round 702, Div 3. I'm already a bit late, so just kicking away here. Started 2 minutes late. Oh, this is actually C. Positive. Okay. Oh, we can move. Oh. Who is this muffin head? What? Nobody is this fast. You can't even read this problem that fast. Problem D. Okay, you're just in Cartesian tree? Yeah. Mm-hmm. Okay, you're just building a Cartesian tree. I guess I should do that in linear time, which is to line us here, but greater for max. Okay, so I should say here. Oh, what's going on? Occasional one. Oh, occasional one. Oh, is it actually just... That is actually what they want. Okay. How does the muffin head solve every problem in 2 minutes? How do you read every problem that fast? Didn't I just have this problem? It's everyone who's not the strict minimum. Oh, that's not right. Got wrong answer. Okay, so I have to. It has to be. Oh, the sum. The sorted prefix sum. Ah, okay. That's what it is. Sort possible. Okay, now does it work? And the key thing is if you have like 3 people and they're like 1, 1, 10, only 10 can win. Okay. That seems more fit. There's no way you can do that problem in 2 minutes and then do F in 2 minutes. It's ridiculous. I don't know, maybe they're legit, but I just feel very skeptical now. Oh, it's looking wrong on this. No, M. Okay, yeah, we're just gonna, okay, so now. Alright, so that's basically the amount we get to save is like F minus I times, so that should be pretty simple. Oh, A can be negative. Oh, wow. This doesn't seem that hard. Okay. So I think it's the idea is like take the previous sums, find each new max, and then yeah, okay, so okay, so basically we're just gonna search maxes. than it happens the first time. Search. So we're just going to do loop round. Make pair with X and 0. That's when it happens. Wait, so yeah, okay, so then otherwise if n is greater than 0, if it's not greater than 0, so if it's greater than 0, then what is this? What am I doing? Okay, so need is going to be something like tell me we need. I don't know. Seal divide that by. Seal divide that by. This is going to be seal div of this, and looks like n. That's times when we go fully around. So x is minus equals fold. Now surplus is minus step back to first, and then plus equals 4 times n. All right, that's it. From there, okay, so let me see. Oh, I don't want seal div, I actually want floor div. So what am I doing? Okay, no. I don't need this. Oh, wait. I do want seal div. If I like 7. 2. Oh, I do need seal div. What am I doing? Okay. So why am I getting too many? Oh, what am I doing? No. It is, oh, I see. It's like this, except not. Okay, that should be right. All right. Okay, cool. Finished. sitting in 4th place right now, but pretty bad penalty. Probably will keep dropping down. Starting 2 minutes late cost us a lot. It cost us 2 minutes on every problem, so that would be 85 penalty if I hadn't, but Colin would still be 2 minutes ahead of us. So good stuff there. And then Muffin Head, I'm very confused, because if you can solve all these problems in 2 minutes, you know, why can't you solve this problem in 20 minutes? Seems kind of odd, but anyway, we can go over some quick solutions here. So, okay, yeah, I thought A was weirdly difficult. This is really not what I'd expect from a Div 3A. But basically, you need to make sure that the array satisfies any 2 consecutive elements. They differ by a ratio of no more than 2. And then you can insert numbers to make sure that's the case. And so it ends up being it basically ends up being that you take the ratio between the 2 and you just kind of find the smallest power of 2 that is at least as big as this. So for example, if the numbers are 2x apart, like 5 and 10, then you're fine, you don't have to do anything. The ratio here is 2.2, and so then your power of 2 would be 4, and so you need to reduce that to 2, so you need to do 1 insertion. And then, you know, if you had, let's say the numbers 2 and 14 consecutive, then your ratio is 7, and then you need to round up to a power of 2, which is 8. And then because 8 is 2 to the power of 3, we need to do 3 minus 1, which is 2 extra insertions. Yeah, you can imagine kind of if we had 1 and 8. So this would be kind of the worst case for the power of 2, 8. Is that you have numbers that are actually 8x apart, and what you can do is you can insert 2 and 4, or in this case, you know, 4 and 2, and that way you keep the 2x ratio. But yeah, this is not what I expect from a Div 3A. This seems quite hard. Anyway, so add that up and then print that out. Okay, let's see, what else do we have here? Yeah, and then this just seems a little weird to me. Like, Div 3A is quite hard, and then B is already a big drop in solves from A, so B is also quite hard. I think the early problems in this set are a bit questionable in terms of difficulty. Okay, but problem B, basically we have n divided by 3 and we have an array, and we need to make sure the number of elements 0 mod 3, 1 mod 3, and 2 mod 3 are equal for each of those mods. The only thing we can do is take a number and replace it with 1 larger. So that moves it either from 0 to 1, 1 to 2, or 2 to 0 mod 3. So yeah, all we do is we just grab the counts, and then yeah, count the 3 mods, and then I mean, in my solution, I know the goal is n over 3, and then for any ci that's greater than that, I just kind of grab it and move all of the extra to the next one. And I just do this in a loop until it's over. This loop should happen at most 2 times, I think, so it'll be fast. But yeah, it's basically a greedy idea. I mean, the thing is, you can think about it as, if you have 6 things, oh, hang on, let me close the door. You know, if you have 6 things that are 1 mod 3 and you need to have 4 things, well then you definitely have to pick 2 of them and bump them up by 1, because you can't, the only way you can reduce the number of things that are certain mod 3 is by taking some of them and incrementing. You won't be able to reduce by taking other ones. So yeah, we just kind of greedily do that until we're done. And just make sure to break the loop when everything is equal. And that's what this is for. It's kind of a little bit hacky, but it's fine. The Boolean kind of just functions as our loop. I could also just, I could have done this instead, which would be a little better. False, and then while any, and that should be fine. Yeah. Okay, problem C. Right, problem C is sum of cubes. You're given x up to 10 to the 12th, and you want to know if there's two integers a and b where a cubed plus b cubed equals x. Yeah, and so this is actually pretty simple. The key insight is that if x is up to 10 to the 12th, then a and b have to be up to 10 to the 4th. Because if they're bigger than 10 to the 4th, then, you know, if a is bigger than 10 to the 4th, then a cubed is already bigger than 10 to the 12th. So, and then the other thing is that if we figure out what a is, then we can just solve for b. Because basically we just loop up a from 1 until its cube is too big. Then b cubed is going to be x minus a cubed. And then we just use pow to find the cube root of that. I use round just in case we have some precision issues. So maybe if, for example, you might take, since you know 1/3 is not going to be precise, maybe it's possible you take 27 here and you get like 2.99999, something like that. I don't know if that's exactly what happens, but this is a possibility. And so if you just cast straight to an int, you'll get 2. That's why we use round here. And then we just check if b times b times b is actually b cubed, or actually the b cubed we want, and also make sure b is greater than 0, so that way we don't allow b equals 0 because the problem requires positive. And if both of these work, then the answer is just yes. Otherwise, it's no. So pretty simple one there, but it's just recognizing that this loop is fast enough, and then that you need to be careful with the floating point and round to avoid any issues there. Okay, problem D. Okay, right, problem D involves basically you build the Cartesian tree on the array. So this is the same tree idea. This is the min version, the min heap version. In this problem, they give you the max heap version where the biggest number is on top. So yeah, I already had some code to build Cartesian tree. It actually built it in linear time with a stack. So I just called that code, and then in order to get depth, I actually did depth in n squared, which is kind of funny. But in order to get depth, I just start from location and then keep going to my parent until I get to -1, and then I output that. But in this problem, you know, the constraints are real small, only up to 100, so you don't need to worry about building it in linear time. You know, just find the max, set that as the root, and then recurse on both sides, and you should be fine. And that way you can just build everything and then calculate the depth as you go, and it should be pretty smooth if you do it in a nice way recursively. Okay, just moving right along. Problem E. What's this? Oh, this one I got a wrong answer on. Yeah. So for this problem, we're trying to figure out who can win the entire championship. And then it's a process where 2 random players are picked, and then the player with more tokens wins and kind of eats the loser's tokens, or like takes all the loser's tokens. If they're equal, then it's just random, either one can win. We want to know who can possibly win. And so basically, we always know for sure the person with the most tokens can always win, because they can, I mean, they'll just beat everyone if they go immediately up against them. Or they can at least. And for anyone who's not the biggest, the way we can look at it is, well, what kind of procedure should they go through to win the thing? Well, it basically looks like this. If we take, for example, if we take this and then let's sort it. So let's say these are the tokens people have. Now for anyone, let's say for example this one, what they should do is they should just eat everyone to the left, basically beat everyone to the left and then take all the tokens, and then you'll end up with this situation. And then from that point they just need to keep pushing right as long as they can. So we'll get this, and then we'll get this, and then they will succeed, we'll get to this. So if you think about that, then what it means is that for this person, what we need is that this prefix sum is at least this number, and then this prefix sum is at least this number, and then this prefix sum is at least this number. And that's the conditions we're checking here, basically. So yeah, that's basically how I set my code. Read an A, make a sorted list, get the prefix sums of that list, and then we know for sure the biggest one is possible. And then for the rest, because this person needs the prefix sums to work all the way through here, this person needs all the prefix sums to work, but like this person only needs one prefix sum to work. We just start from the right and go left until something doesn't work, and then that's the range of things that works. So that's just what we're checking here. We're just checking that the prefix sum is at least as big as the value. And if so, we just continue going left and then add the new index. Then make sure to sort, and then just output everything. Okay. Let's see, we'll go to F and then G. So for F, basically we want to remove things from an array until every value that does show up in the array occurs an equal number of times. We want to know the minimum number of things to remove in order to do that. So for example, for this, we can remove 3 and 4, and we can get this. We can remove a 1 and a 2, and we can get this. And so we have different options. The answer for this one will be 2. Basically, it turns out that you can just calculate the frequency table of your array. So for this array, we don't actually care about the order or the values themselves. We just care that, okay, there are 2 things that show up once, and there are 2 things that show up twice. So that's what we do here first, right here. So we have frequency map, and then this tracks the frequency of each thing. And then from that map, we just make a list of all these frequencies and then sort them. And then the key idea is, if we pick a number that, if we pick the number C here, that we want everything remaining to have a count of, then we'll know exactly how many things we can end up with. It's just the number of different values that have a frequency of at least C, and then that number times C. So for example, if you want to end up with everything having a frequency of 2, well, we know there's only 2 values here, 1 and 2, that have a frequency of at least 2. So it's just 2 times 2. And then in general, if we pick frequency I as the cutoff, then basically f minus I, the suffix, so that's the number of things, the number of indices in the array that are I or later. We multiply that by the C, which is frequency I, and that's how many things we can keep in this version. And so this is n minus that is how many things we discard, and so we consider that as an option and take the best one. Okay, and just kind of powering through these. So the last one is G. For G, we have this spinning disk situation, and it's for some reason, the floppy drive just adds up numbers as it spins. And we have queries about when is the first time we'll reach a certain number or bigger. Okay, and yeah, in this problem, the key thing to think about is if the sum of all n numbers is greater than 0, then we can get to any x eventually, right? Because every time, as we go to infinity, basically the sum will go to infinity. And then if it's 0 or smaller, if it's less than or equal to 0, then going around the drive more than a full revolution doesn't help, because any number that we get that way is less than or equal to just if we had done just the prefix of the drive. So those are kind of the two cases. The other thing we need to know is, so the AI can be negative. So the other thing we need to do is kind of pre-compute the maxes of the prefix sums. So that's what we do here. We find all the prefix sums, and then we take the maxes. So basically, as long as prefix sum I is greater than the last max, we will include this one. And yeah, in that case, basically if we know we can get to x by at most one revolution, then we can just do this lower bound in the maxes. So we just binary search the maxes for the first thing that's greater than or equal to, and then we take its index. Otherwise, the only way we can get it is if prefix sum n is greater than 0, so the sum of everything is positive. And that way we can decide how many full revolutions we need to do. Basically, how many times do we need to add this value before we can actually reach one of the maxes with a single partial spin. And yeah, so we do a ceiling division here of kind of this gap, x minus the maxes, or x minus the max. Divide that by prefix sum n. That's how many full revolutions we need. And then we can remove that from x, and then we kind of do the case above here, just this again. Because that way we know how long is kind of the partial spin at the end. And then we add full times n. And finally that gives us our answer, and that's it. Okay, so that's all the problems. And oh yeah, just make sure to print -1. That's all the problems. Let's look at the standings again. Wait, so this is very weird. I don't really see why Muffin has not done problem G yet. But the crazy thing is they still have about 10 minutes to get it and get first because of ICPC penalty. Because if they did it 10 minutes from now, they would get 57 points, and then that would be I guess they would get 56. And that would give them 82 penalty, which is enough for first. So even though that's so much slower than all of the top 10, that does land them in first because of ICPC. I've always thought ICPC penalty is kind of stupid. It matters so much how fast you do the first problem. Like the first problem, the amount of time you take on the first problem is weighted by n, the number of problems, whereas the amount of time you take on the last problem only counts 1x. So kind of a very silly system. It hurts me pretty bad for showing up a couple minutes late. But anyway, I guess we'll see if they manage to get there. And otherwise, if not, congrats to Colin for a really nice win. I mean, either way, it'll be first or second place. So congrats either way. But okay, I think that's it for this video. Gonna end it now and see you in the next one.